Hey physics kids, this is Mr. Galoya coming at you. Hey, hopefully you're doing well today. Hey, I wanted to work a few practice problems for you on energy conservation. And right now I've got this, I've got my document camera here, and let me kind of make sure that you can see that perfectly fine. Okay, so basically we've talked about different types of energy, and some of the common forms of energy that really kind of deal with motion would be kinetic energy, gravitational potential energy, spring energy, and I've got the equations really for those three here. EK 1/2 mv squared, EG mgh, and the spring or elastic energy 1/2 kx squared. We also have dissipative energy. We really can't get rid of energy due to friction or dissipative effects, but we often kind of ignore that in many of our calculations. And typically we also can maybe discuss what's called mechanical energy. Mechanical energy is the summation or addition of kinetic and gravitational potential energy. So I've got really several different types of problems here. And so energy conservation really involves looking at the energy that an object has kind of before an event and then after an event. Or you're looking really at the energy of the object at two positions, really. And so in this first problem, we have this 56 kilogram cliff diver, so that'd be the mass. And the diver then runs to the edge and dives off the edge into the water 4 meters below. If she's moving at 8 meters per second, so that's a velocity, horizontally, the instant she leaves the cliff, make a drawing and then determine her following. Her GPE relative to the surface of the water when she leaves the cliff, her kinetic energy when she leaves the cliff. The addition of this would be her mechanical. And then we really want to look then at her energy then when she enters the water. And then her speed. And we can use then the idea of energy to actually come up with the answers here. So what do we really have here? Well, we've got this cliff diver, and we can maybe just draw a cliff. And the cliff diver then is running. And so the cliff diver then has the kinetic energy, EK, but the cliff diver also is at a certain altitude or height above the water. And so the cliff diver also then has an EG that's based on her position. So she's got both of these initially. There's no springs involved, and so we don't need to worry about, or elastic material, we don't need to worry about elastic energy. And she's going to kind of come off here. It'll be really a parabolic motion here, but she's going to come off, and she's going to enter the water at this position. So we're looking really at position 1 here, and position 2 there, or point 1, point 2. And point 2 then, this gravitational energy that she had will be converted then into potential. Into more kinetic energy. So she's going to basically have kinetic energy because of her horizontal motion here, and she'll have even more kinetic energy because now she's got that horizontal velocity and she's got vertical velocity. All right, so that's basically kind of conservation here, that she's got a type of, so she's got some energy at point 1 or position 1, and then she'll have energy at position 2. Now, there really will be some dissipative effects of atmospheric friction and air resistance, etc., but we're basically going to ignore that. So we would say the summation of this is going to be equal then to her total EK here. So let's get then right here her MGH relative to the surface of the water. That would be her UG, or E sub G. So we would say then the mass times gravity times then her height and she is 4 meters above the surface. So we'll basically just calculate that out. 56 times 9.8 times 4. Okay, there's basically the answer here. So that represents the energy in joules she has based on her position above the water, which is often our reference point. Well, she also is moving though horizontally, so she has an EK, or a kinetic energy, that's based on that horizontal velocity, 1/2 mv squared. So that would be 1/2 times, again, her mass, times her square of her velocity. Okay, so put that in a calculator, 1/2 times 56 times 64, and we get 3584. Oh, I missed it. Hold on. 1/2 times her mass times her velocity. Oh wait, I did the calculation wrong. My calculator, I can see I missed. I didn't put the half in. 0.5 times 56 times 64. 1792. There we go. Okay, so we're basically saying then that her mechanical energy is a combination of these two. We can sum those up. So 2195.2 plus then 1792. And that's going to be then this 3987.2 joules. So, barring any dissipative effects, which we're going to ignore in this problem, barring any dissipative effects, really, then this mechanical energy will remain the same. So her total energy remains the same throughout this trajectory. So then we'd like to get her speed then when she enters the water. Well, she's got all of that energy here. So this is her total energy along that trajectory. And that's going to equal then to 1/2 mv squared. So energy, again, is conserved. This total mechanical energy is the same along her trajectory. So at this point here, then all she will have left is EK, because she is now at that reference point, and that M would be 0 here. So this will be 3987.2 joules equals 1/2 times her mass times the square of her velocity. Okay, so we would take then that, basically take her mechanical energy, 3987.2, multiply it by 2, divide by 56, and then take a square root. And I get around 11.9. That would be then in meters per second, 11.93. Okay? So notice we didn't really need to, in this case, we didn't really need to know, Newton's laws, really, F equals ma. We're doing this really in an entirely different kind of way, using the properties and the ideas of energy and energy conservation. All right, so that represents the first problem. Okay, well, let's take a look maybe at the second problem here. So, an arrow is shot at the apple atop the head of Walter, William Tell's son. The arrow is 0.2 kilos, so that's the mass of the arrow. It's moving at 20 meters per second, so that would be basically the velocity, meters per second. The velocity then that the arrow had, meters per second, the velocity. And it's shot 1.5 meters above the ground, so that would be the height above the ground. So you might say, well, is there any sort of spring energy here? Well, there would be elastic energy in the bow, and that gets the arrow started in its velocity. But basically, we want to analyze the arrow once it leaves, basically, the arrow is moving it when it leaves the bow. I think that's a misprint there, when it leaves the bow, and is shot so many meters above the ground. So we are looking at the arrow after it leaves the bow, after it's been given that velocity by the string. So the arrow might do kind of something like this, where it's kind of doing something like this. We don't really have a complete picture here, but there's the apple here. And we don't really have a complete sort of diagram, but we can envision maybe the arrow taking some sort of a parabolic motion here. And the arrow then has a velocity, and the arrow has a height above the ground. So the arrow is going to have then kinetic and potential energy. It's going to have mechanical energy, and that energy is going to be conserved again as long as we don't need to worry about any dissipative effects. So initially, then, the arrow is going to have EK and EG. And then we want to get how high above the ground does the arrow strike the tree. If it is moving, I guess, moving at 10 meters per second at the instant it strikes the tree. So it's going to have both of these types of energy here, but they're going to be a little different. So the arrow is moving at 20 meters per second here. It's moving 10 there. So the arrow is going to go up some sort of altitude that's going to represent changing some of that EK, changing some of that EK into more EG here. So we would say EK plus EG at this position, that's going to be equal to EK plus EG at this position. Now we really would have a little bit of dissipative effects, but we don't really need to include that because we're just going to ignore that here. And we don't really have any sort of spring energy because we're dealing with the arrow once it's in flight, or once it just leaves the bow. So we would say then 1/2 mv squared plus mgh, that's going to be equal to 1/2 mv squared plus mgh on this side. So all this would represent that total mechanical energy. So we'd have the mass, that's 0.2 kilos, times that velocity, 20, we've got to square that, plus mg, 1.5 meters. So that's going to be the mechanical energy. So let's put that in our calculator. So 0.5 times 0.2 times 20 times 20. Okay, so that's 40. And then we'll add that to 0.2 times 9.8 times 1.5. So 42.94 then represents the total mechanical energy when it leaves the bow. So that's going to be the same amount of energy it has here. Okay, position 1, position 2, energy is conserved. So 42.94 joules here, and that's going to equal then to EK plus EG at that position, or 42.94 joules equals then 1/2 mv squared plus mgh. Okay, that's going to equal to 1/2 times 0.2 kilos times 1/2 mv squared, and the velocity we said was 10. Square that. Plus 0.2 times 9.8 meters per second squared times h. And that's what we want to get, the height above the ground. Again, the baseline height is the ground. So we've got 42.94. And I'm going to subtract then 25 times 0.2 times 100. Okay, so I've got 32.94 left. I'm going to divide it by 0.2 and divide it by 9.8. And that gives me a height of around 16.81. Okay, that's the answer there. So the height, 16.81 meters above the ground. 16.81. All right. So basically, we gave up some kinetic energy here, and that kinetic energy was transformed into EG, or some of that kinetic energy was. Again, conservation of energy. Okay, so let's move on to the third problem. Are you kind of getting the handle on it? Basically, we're taking the types of energy it has at one position and equating that with the types of energy at the second position. And we're, again, neglecting air resistance, any sort of dissipative effects. So in this case, we've got this snowmobile. There's your mass. And it's traveling with this velocity. Okay, so the snowmobile then comes to a small cliff that's 2.5 meters above the ground. So basically, the snowmobile is going to then move in a trajectory that's basically parabolic. Okay, it would be, once it leaves the cliff, it's going to be in free fall. The height above the ground is 2.5 meters. So at this point here, at this position here, we have kinetic energy, and we have then gravitational potential energy, or U sub G, or PGE, or whatever symbol you want to use. It's got then kinetic energy. At this position here, then, it's given up this UG, and it will form then additional KE. So its KE is going to be larger here. Okay, in fact, the object's going to have that horizontal velocity, but also coupled with that horizontal velocity, then will be a downward velocity, because it, again, is in free fall. Again, there's different explanations, different ways you can explain this idea. You can talk about the idea of the snowmobile in free fall, and something in free fall, as it moves down, gets faster and faster. We can talk about the same sort of trajectory, though, with energy, or energy conservation. So the total mechanical energy, as he leaves the cliff, that's going to be then our KE and mgh, 1/2 mv squared plus mgh. Okay, so 1/2 mass, 300, times the square of the velocity, 16 meters per second squared, plus the mass, that should be 300 kilos. 300 kilos times gravity times the height, that's 2.5 meters. Sorry, I can't get all that in there. But we have a product, 1/2 times the mass, 0.5 times 300. Okay. Times 16. Okay, there's your kinetic energy, plus the mass, 300, times 9.8, times 2.5. We'll add up all that, and that becomes the total mechanical energy, 45,750. Now we know then that the snowmobile will have that same amount of energy throughout that trajectory, as long as we're going to neglect any sort of air resistance, okay, any sort of dissipative effects. But at this location here, then, that UG now is going to be gone. So it's going to be this total will now be equal in joules, will be 1/2 mass times the new velocity squared. Now that new velocity really is going to be a forward and a downward velocity, but again, it's going to act tangent to the trajectory. So it's going to be basically the hypotenuse of that velocity triangle. Okay, so again, we want to solve for that velocity. So we're going to multiply this by 2, divide by 300, and then take a square root. And I get about 17.5. 17.46. Okay. Okay, that's done with problem number 3. Okay, well, number 4 is kind of a classic problem. It really deals kind of with the idea of a pendulum. So in a pendulum, we have this swing, and this pendulum then creates kind of an arc, and the in a frictionless sort of pendulum, if we could have this pendulum with no friction, it would go from, UG, and if we call this in our baseline, it would maximize the kinetic energy here. So potential energy to kinetic, back then to UG. And it'd be kind of swinging this arc back and forth, and we basically have this kind of a classic interplay of energy. At the sides here we have no velocity. All the energy is potential, gravitational potential. And as the bob or the pendulum then comes down, that UG is then transferred as velocity or kinetic energy. And at some point in between, we have some of both types of energy. So that would be really what would happen in a frictionless or friction-free, no dissipative effects pendulum. In a real pendulum, though, there's a little bit of friction and air resistance, and that over time, the back and forth motion will settle down until finally it's not going back and forth anymore. Well, in this case, we have my two boys here playing on this swing, and basically Casey's got a mass of 40, and he's got a velocity of 8, so there's your mass, and there's your velocity. So he's basically running along the ground here within a kinetic energy, and he goes towards the swing, catches the swing, and then kind of goes up. And the swing then, as he's on this swing, it keeps going up along this arc until then he then reaches this maximum gravitational potential energy, and his kinetic energy then would be 0. So we have this position here, and if we want to call this our baseline, then our UG or GPE at this point is 0. So all we have initially is KE, and then in the second position we're just going to have GPE, or U sub G. So we want to get basically how high Casey gets above the ground. Okay, so we would have a kinetic energy, 1/2 mv squared, going to potential energy. And we'd like to figure out this height here. Okay, there's our unknown right there. All right. So again, a classic sort of energy conservation idea. In this case, we have mass on the same side here, and they cancel really. And we have 1 1/2 velocity. That would be 8. We have to square that. That's going to equal to 9.8 meters per second, and meters per second squared h. All right. So on the calculator, we would take then 8 squared, 64, times 0.5. Okay, there's 32, that's this side. Divide that by 9.8, 3.26, okay, or 3.27. So the height then is 3.27 meters. So Casey's kinetic energy then, takes that swing up to the height then of 3.27 meters above the ground, all right? Now Ryan, younger son, is a little bit lighter in mass. So in this case, this problem kind of works backwards a little bit. So he basically, I know the verbiage here. He runs, okay, with some velocity, and the swing then gets 3 meters up for him above the ground. We'd like to know then how fast was he running to achieve this height. All right, same idea here, 1/2 mv squared. That's going to equal then to mgh. In this case, we don't know what that velocity is. Okay, the masses again cancel. We're left with 1/2 v squared equals 9.8 meters per second times 3 meters. Okay, so 9.8 times 3 times 2. Okay, we'll take a square root. Oops. Take a square root. I get about 7.7 or so, 7.7 meters per second. Okay, this is kind of a classic problem that's kind of based on the motion of a pendulum. Okay, this next one is kind of a classic problem, sort of too. We basically have a slide at an amusement park, and the top of the slide is 6 meters high. So you guys have seen these slides kind of at the amusement park, maybe these water slides or whatever. And in this case, the people go up 6 meters above the ground, okay, and then they kind of slide down. Maybe they go into the water or whatever. And we'd like to get the speed attained at the bottom of the slide by a 30-kilo child. That'd be the mass, and that'd be the velocity. Now we're assuming on this part that the child starts from rest, so there'd be no kinetic energy here, so all we have is UG, or GPE. And at this, we're at the baseline, at the ground, so all the energy would be KE. And basically, in this case, we're ignoring this first part, we're ignoring any sort of friction that might exist on the slide, okay? And so we'd like to get then how fast the child's traveling at the bottom. So we'd like to get the velocity here, okay? So we'd have then GPE, or UG, at the top here. That's all going to be equal to KE here. So that would be then KE, or MGH, equals 1/2 mv squared. Okay, so notice the masses here again cancel. We have 9.8 meters per second times the height. That's meters per second squared times 6 meters. That's going to equal to 1/2 times v squared. All right, and so let's determine the velocity. Okay, 9.8 times 6 to the times 2 to the square root, get about 10.84. Right. Now, a more realistic problem would be basically if we could repeat these calculations, but we assume then that we get some of the energy lost. We basically get some of the energy, the GPE lost, or is lost to friction basically. It's therefore dissipative energy. So we could probably say here then that GPE really is equal to KE plus any dis. So in this case, we're assuming that 80% of this GPE that the child had at the top is required to overcome friction and is therefore dissipative energy. So now we'd like to redo our calculation, but determine really a more realistic velocity for the child, assuming that 80% of that GPE actually goes into motion. So basically what we have then is, we could say, well, that means 20% would go into motion, or 20% is 0.2, right? 20% of MGH goes to 1/2 mv squared. Same sort of calculation here. So I take 0.2 times your 9.8 meters per second times the height of 6. That's going to again be 1/2 v squared. So 0.2 times 9.8 times 6 times 2 to a half power, about 4.84, 4.85. All right, kind of a classic problem, 4.85. All right. Okay, we're on to page 6 now. And let's do a few problems here. I think the rest of the problems kind of deal with spring energy and how we might be able to kind of use that in our calculations. Now, spring energy is definitely definitely a little bit different. So we talked about kinetic energy, we talked about gravitational potential energy, and spring or elastic energy is a type of potential energy. And what we're doing is we're basically you know, I'm doing work now like on the rubber band, and as I stretch the rubber band, then energy goes into the bonds, and you know, a stretched rubber band then has energy tied into those bonds, potential. And like we said, we could maybe make a catapult. You know, we could propel. You know, we could propel something with the rubber band or with the spring or something like that, and so we can use that trapped energy to give an object kinetic energy, or to maybe fling an object up into the air above the ground, giving it potential energy. Now, spring energy is in a kind of a similar, so kinetic energy is 1/2 mv squared. So if we were to graph then kinetic energy of an object and its velocity, we would have then a parabolic relationship because of the v squared there. You know, if we were to graph mgh, you know, potential energy in height, it would be a linear function. So as you go up in height, 1 meter, 2 meters, you know, assuming that g stays somewhat constant, which it changes a little bit as you go up above the Earth's surface, but if that g stayed constant, you know, we'd have a linear function. Well, spring energy, okay, U sub s, or E spring, or E elastic, that basically is also a parabolic relationship. It's 1/2 k delta x squared, okay, where this delta x really represents how far we're stretching that spring or that rubber band or that elastic material away from its original sort of position, or its non-stretch position. So that's going to be then quadratic also, if we were to graph in that change of position and the spring energy here on the y-axis. That'd be quadratic also. And that's kind of what this problem is really dealing with. So basically, during which interval is the largest amount of energy required to stretch the spring. And we're going from its equilibrium or rest position to distance, or from d to 2d, or 2d to 3d. So which interval represents the highest, you know, this largest amount of energy, work that I have to put in, or energy I have to put in to stretch the spring. It could be a spring, it could be a rubber band, it could be any sort of elastic material, all right? Now, so again, spring energy represents then 1/2 k delta x. So what we can say is the change of this energy, or spring energy, would be then 1/2 k times d squared, okay, or delta x d minus 1/2 k times 0. Okay, that would represent then the first interval, or this first one right here. Okay, remember what the k value is. It's called a spring constant. Okay, it's a spring constant. It basically is a constant for that sort of material, or for that spring or rubber band. All right. So we could say here, then this term goes away, and we'd be left with 1/2 k d squared. Okay, that'd be the value of the energy that you would have to put into the spring to stretch it from here to there. Now, if we do this one, we're going to have 1/2 k 2d, but that 2d has to be squared, okay, minus 1/2 k, then d squared. All right, so that's really 1/2 k 4d squared minus 1/2 k d squared. Okay, so this is really 2k d squared minus 1/2 2k d squared minus 1/2 k d squared. That's going to then be, what, 3/2 k d squared. Okay? Notice that amount of energy here is larger here. So it takes more energy to go from here to here than it does to go from here to here. Now what about 2D and 3D? So already we know it can't be this answer, right? So now let's check this. So 1/2 k times 3D squared, so that's really 9D squared, minus 1/2 k, we're looking at 2D, so it's really 4D squared. So again, I squared the 3D, quantity squared, that'd be 9D squared. So this is really going to be 9/2 kD squared minus 4/2 kD squared, and that's going to be 5/2 kD squared. All right. So this would represent the largest amount of energy. So basically, what would this, if we could basically graph, we know it's going to be parabolic, but if we had D, 2D, 3D, 4D, something kind of like this, parabolic, where we're looking at energy, ES or E, elastic energy. So from here to here, there's not too much energy. Here to here, more. Okay, you see this, it's this vertical line, really. This vertical line here that we're actually analyzing, right? And the interval, from one point to the next point, or the interval here, that difference amount of energy is growing. And the reason really because of that is because of the parabola, or the parabolic nature of the graph. All right? Well, this didn't really involve any sort of conservation of energy, but it did involve just determining some spring energies. Let's do maybe the next one. Okay, that would involve a spring also. So we have a vertical spring with a force constant, so there's a K value of 200, so that's our K value. That's 200 newtons per meter. It is compressed 8 centimeters. So this is your delta X. That'd be 0.08 meters. Okay, so we're taking a spring, basically compressing it. So now there's spring energy here. We place this ball, the mass of the ball there. We place this ball on the spring, and we release the spring, and it flies vertically upward. So the ball goes up, up, up. Basically, you could say, well, its spring energy is being translated into kinetic, but then there is a point here that the object then it's in free fall upward, and gravity has slowed the object, and now the velocity is 0. And we have then just potential energy, or U sub G, right? So we have spring energy going to U sub G here. So basically the gravity pulls down on the ball, slowing it down. So the ball's traveling upward. The ball's traveling upward with the velocity. Okay, it's in free fall going upward. And eventually gravity slows it down to a point then that ball has stopped, where its kinetic energy is 0. Okay, how high does the ball go above the top of the compressed spring? So we're going to call this kind of our reference point. So we're going to make this level, our UG is 0 line. And so we're basically saying at this point here, at this position here, at picture 1, all we have then is elastic energy, or spring energy. At this position here, position 3, okay, it has no velocity. All it has then is U sub G, or GP. So we would have 1/2 K times delta X squared. Okay, that'd be the compression of the spring and the spring constant. That's going to equal to mgh. All right? So again, energy conservation. Now there would be a little dissipative effects in the spring and air resistance, but we're going to again ignore that. So we have 1/2 times 200 Newton meters times 0.08 meters. We need to square that. That is equal to the mass of the ball. 9.8 meters per second squared times your h. Again, spring energy would be in a joule sort of thing. Okay, so let's just check it out here. My batteries are running low on this calculator. So 1/2 or 200 times 1/2 times 0.08 times 0.08. Okay. I'm going to divide it by 0.35. Divided by 9.8. And get then an h of about 0.19, 0.1865, 0.19 meters. That's about 19 centimeters or so. Okay, 19 centimeters. So the ball goes up about that far, whatever. And so 0.19 meters, or about 19 centimeters. Okay, see how that all kind of works? Let's just do one more maybe. This would be our last problem. So let's say this box, so we have a box that's sliding on a frictionless surface. It's got a speed of 15 meters per second. So there's its velocity, there's its mass. Okay, it approaches a horizontal spring. The K value is 2,000. Now we want to know then, how far will the spring be compressed when the spring is partially compressed and the box speed is reduced to half its initial speed? Okay, so this is the unstretched spring, and as this box plows into that spring, okay, the spring will eventually, if possible, the spring will eventually stop it. But we don't want that position. We want the position when the spring is partially compressed and the box spring is reduced to half. So that would be, what, 7.5 meters per second would be the velocity. So that's going to be in the middle here, some intermediate sort of placement, really. So initially, position 1, all we have is kinetic energy. And then at position 2, we're going to have kinetic energy and then some spring energy. Notice we have no change of altitude here. We don't really have any sort of gravitational potential energy. So we could say, well, 1/2 mv squared, that's this, that equals to 1/2 v squared plus 1/2 k times delta x squared. Where that, again, that delta x represents the compression. All right, so we would have 1/2. Now notice, though, the halves, we have a half basically in every term, so it cancels. We have the mass, let's see, 1.5 kilos, times the velocity, 15 meters per second squared. Okay. 15 meters per second quantity squared equals 1.5 kilos times the new velocity, plus then 1/2 k, the half's gone, k is 2,000 meters per meter, times then the delta x squared. All right. So on a calculator, we would take 1.5 times 15 times 15. Okay, so that's 337.5 joules. 1.5 times 7.5. Squared, that's 7.5, 84.375 joules, plus 2,000 times delta x squared. And make sure that's all in there. Okay. So I'm going to take my 337.5, subtract that from 84.375. Okay. I'm going to divide that by 2,000. Okay, I get then 12.65. That's delta x squared. We need to take a square root of that. I'm going to take a square root of that first. Take it to the half power. get then delta x is 0.355357, or I've just rounded it off to 6 meters. All right, so basically what happens is, as this object then encounters the spring will be compressed by this much, and at that particular a picture right at that position, the box would have a velocity then of 7.5, and the spring would be compressed by that much. If we basically gave the spring more time to work on this, then the spring would probably stop the box. And we could actually determine that. So we could basically say, well, if all this energy here, 1/2 mv squared, goes to spring energy, all right, and the halves again cancel. I'm just going to leave the units out here this time. Okay, we would get 1.5 times 15 times 15. Divide that by 2,000. Take the square root. You get about 41. 0.41. So 0.41 meters. Okay. Now remember, spring energy is not linear. All right. So, okay, so that basically represents kind of potential kind of conservation of energy problems, potential energy with kinetic energy, spring energy, etc. Okay, we'll talk to you later, kids. Bye.